Welcome to the class Aerosol and Nanotechnology. Today we will have the topic of aerosol and nanoparticle characterization. The slides are not uploaded yet, but will be uploaded, and for the other ones I will try that you have them before, okay? So the schedule or the outline for the class, for those who weren't here last week or have to be reminded, last week we had the introduction. The slides are online, right? The introduction slides? Okay, very good. And today we will talk about aerosol characterization, which will be a very, how we say, dense topic. You will see it during the lecture. It's highly related to just one thing. And then we will have 2 weeks of break because it's Easter time and I will be also lecturing somewhere else. And afterwards, we will go into a main part of this class, and this is the transport of aerosols, something I really, really like. And it will get a little bit mathematical at this part. Today, not so much, so you can lean back a little bit more. Then we will look into light scattering. I will ask anyway later, but whom of you had lectures about light scattering already? Yeah, which lecture? So you also go in the lab and do light scattering experiments there? What kind? So spectroscopy of what?
There was some coatings and we just...
Do you want to see the thickness of the coating or the... Okay. So you change the particle or you change the color property and you investigate this. Okay. What kind of materials? Yeah. Okay. Okay, so you make nice paints. Is anybody of you painting, by the way? Like hobby? Yeah? Okay, just... But you don't like painting by yourself, or you do? Like a hobby or something? Okay, because in the last class we had somebody who did it, and then we bought some special material, and he made kind of really, really amazing paintings for a project work. So this is why I'm asking for it. Okay, then there's a class called Experimental Methods, and there we look a little bit into things we could use in the lab. And today we will touch this already, and there we will repeat it a little bit, but I think it cannot be repeated often enough. So there's already a link from this class to this class. And then later when summer begins here, while summer not really begins in Germany, but that's another thing, we will talk about coagulation, gas-to-particle conversation. So this is really engineering part, and then there are some more fun lectures at the end. Well, that's already quite a theoretical lecture. And then we are done with the class. Okay? For today, promising empowerment. I promised you that I will always show you this slide to just repeat you why you are here, what we are doing here. And you should get an overview about aerosol technology. I hope last week this already started, right? We had a very important material last week for aerosol technology. Who reminds which one? Yeah? Carbon black, right? And this is also to the third point. You have an idea about the technical application of aerosol technology. Why carbon black was interesting when it comes to technical applications. Yeah? It was used in tires, so it's important in a product. And what else? As an engineer, we not only think about the product, what was also important for carbon black? The manufacturing process, right? We had different manufacturing processes, which we looked at. Do you remind one of them? Very important one. I think it was the third one we looked at. Extremely important in this class, also related to the paper in the seminar. If you now connect the paper, you read for the seminar. Liquid, yeah, it has a different name. I'm not sure if it's, I think you mean it correctly, but the name is... Yeah, that's what you do on the product, but I'm talking about the process. And we had a process which is used in the paper you read, but which was also very important for producing carbon black. Yeah? the flame spray, right? The flame, I think that's what you mean with liquid flames, right? The flame, exactly. The flame process is extremely important, and there we directly have technical applications. And for today, overview about aerosol technology and technical applications have the same points. So it's importance of sizes. Okay, the size is extremely important, and I try to make the point on that today, and also how we work or deal with it. Moving of aerosols will not be much today because we have 3 full, even we have more lectures about it, but it will be touched by some of the technical applications we are looking at. Okay, always try to keep this in mind, that moving is an extremely important part of it. And since it's aerosol and nanotechnology, size. Okay, I think for nanotechnology it's easy. Why for nanotechnology size is important? Yeah? Exactly, because it's nano, right? So it's defined by size. So there we will meet these two together, but no, I will make this point later. We will see something how it's about aerosol with nano size. Good. Another reminder, because it's very important for me, you should remind this slide. What did you remember from this slide? Yeah?
It's a heterogeneous mixture.
Very good. What is a heterogeneous mixture?
It's a one particle of, like, it would be solid or liquid combined with air.
Yeah, exactly. So it's the definition of an aerosol, right? And it's a heterogeneous mixture, could be a solid or a liquid in air or in a gas. While in this lecture, we will be not so critical because we also look at particles in liquids where we can obey the same laws. Okay, we can use the same theory and everything. We don't. This comes more from environmental or health parts. What else? Heterogeneous mixture of particles, which could be liquid or solids. What else did you remind from this slide? Yeah? Ah, the stability. What did we learn about the stability? What do you mean by stability? Mm-hmm. They said don't settle down, right? Or they have to be stable in air for a given time, at least for a few hours. So if I take a piece of chalk and if I leave it, it's by definition an aerosol, especially if I take multiple of them and throw them, but they are not stable. Okay, so this is not an aerosol. Even if I would take 1 million of them and throw them in the air, they would be heterogeneously suspended, but they are not stable, so it's not an aerosol. And the stability in air is extremely important because it means that we can inhale it, for example, right? Because it's very small, and if it's long in the air, I like to go boulder. And if you, whom of you went into a boulder hall already? Were you climbing? Okay, if you go there, you really feel the dust because you have chalk for your hands, and it's like completely, if many people are there and it's really, really stable in the air, you really see it. I always want to take a measurement device with me and measure the loading because you really have this in the air. And the small one, the large one will settle down and the small one will stay, and you see them and then you have them everywhere. Okay, do you remember a number for concentration? We will pick up this later, but we also talked about how many, because I said, okay, I like to go for bouldering, and then there is a lot of chalk in the air. So is it healthy? Is it not healthy? It has to do with the concentration. Do you remind a normal concentration number?
10,000 particles in 1 cubic centimeter.
Exactly, that's the natural loading. So 10,000 particles per cubic centimeter is what's normally here at this point in the air. And for today, I will inhale about how many? Today, I inhale a number of how many aerosol particles at the end of the day? More than 10,000, less than 10,000? More than? What?
I think last time you said it was billion.
Yeah, more than 1 billion of particles, okay? Okay, why the concentration is so important? I mean, we will make a small exercise about it later, but it fits now why it's important. The concentration, I mean, this lecture today is called aerosol characterization, and concentration is one part of the characterization. Why? Yeah?
Concentration defines the health for you.
Exactly. So concentration is extremely important to standards and to health risk, health issue, and so on. Okay, but for aerosol characterization, we need different properties, and it's quite simple. There's only one property which is more important than any other. What could be this property? The most important for aerosols.
Stability.
The stability is related with it. The stability is something which comes out of it, but it's not the main property. No, it's not the charging. That's quite specific. It's a more general property. You probably know from last class.
Density maybe?
No, it's not the density. The density is also somehow related, but this is something we will learn in one of the later lectures. Very simple property. No, you think, I mean, very, very good ideas you have, but you think very complicated. The most important property, size, exactly. So the size is the most important property. And this is something you really have to keep and understand, because I just took the sentence as it is from the book because I like it so much. So particle size is the most important parameter for characterizing the behavior of aerosols. All properties of an aerosol depend on size, some very strongly. Okay? This is a sentence I really, really like. So all of them depend on size, some of them even stronger than the others. Okay. So this means we have to make a full lecture about size. How to describe sizes, what is the size of an aerosol, how to measure the size of an aerosol. And now we have a distinction to nanotech. What is the size range in nanotechnology?
Less than
Yeah, but we don't have a complete uniform definition. But normally we say if one of the three dimensions of a material is less than 100 nanometer, we talk about nanotechnology. But at the end, everybody would agree that nanotechnology is nanometer, okay? But for aerosol, it's not. We have a lot of fine dust, we have a lot of nanometer particles in an aerosol because of the stability, but we even have a lot of micron-sized particles, okay? So we are much wider in the definition. And this is extremely important to understand because the size or the property of an aerosol depends extremely on the size of the particle because the physics is very size dependent, okay? So if it comes to gravity, gravity goes with the radius by, so if I have a particle, I mean, I will need it anyway later, so I try to make it now. And it's somehow a spherical particle. So how does the gravity goes with the radius of this particle?
depends on density.
Yeah, but just for the equation, density is in, volume times density. But how is this dependent on the radius?
So if the radius increases, so
That's correct what you're saying, but how? Times power 1, power 2, power 3, power 4, power 5?
power of 3.
Power of 3, okay? So gravity goes with the radius to the power of 3. And gravity is a volume force. While drag, for example, goes with the radius, you know, 2, to the power of 2, right? So this is a nice, very simple example how the physics changes with size, okay? Because very large particles are affected by gravity and very small particles are not. And in an aerosol, it could be that you have both of them in one size distribution, in one sample, okay? That's a little bit different to nanotech, where your size distribution is not that wide normally, and the physics doesn't really changes within the population or in the same sample. And this is what's here, right? It is important to appreciate how aerosol properties change with size to understand their property. Okay, we have a sample, and it could be that some of them are affected and some of them are not affected, and we will have in the next class a very simple example for this, where we see it, okay? And then aerosol sizes differ from nanoparticle sizes because they also include micron, and don't underestimate, maybe you think, okay, it's nano, it's micron, so who cares? But this is really a game changer when it comes to, here, nature of laws governing aerosol properties change with size. And one example I always really like to give is, so if we want to measure the size of aerosols, I could measure the height of all of you, right? So maybe one of you is 1.60 m, one is 1.8 m. Who's the tallest person in the room? How tall are you? 1.87. 1.87. Anybody is taller than 1.87? Okay, so congratulations. I don't ask for the smallest person. But this is the maximum, right? And let's say the smallest person is 1.60 m, and that's it. And all of you would be in between this. And then we could make an average value with a standard deviation, and that's it. And it's really easy to deal with it, because if you think about the chairs, we can make the chairs in a norm size that each of you fits. Well, now, for aerosol sizes, you have to think they cover more than ranges, and it could be to 10 to the power 6 of magnitudes. Could be, okay? So this means we could have some people here which have the height of 1 millimeter, and then we have some people here which have the height of meters, like you, and then we have some people who have the height of kilometers, and I have to design a lecture room for all of you. So some are much too small for the chairs, some are much too, and this is, right, just keep these in mind. I have to deal with all of them. I have to deal with people who are kilometer large, meter large, millimeter large, and this is what we have to do when we're working with aerosol particles. And I think in this term, you really can see there's a difference if somebody is 1.87 meter or 1.87 kilometer or 1.87 millimeter in height, okay? And this is what we have to deal with. And then there's also, when it comes to production, we would like to have synthesizing methods who help us to make this a little bit narrower, right? To maybe kick the millimeter people out or the kilometer people. And then it's easier to handle. And this is what you see here. I will upload this, of course. And this is, in my opinion, a very, very important slide, which I, in the past, went through quite fast. So here you have particle diameter, and the aerosol books very often use micron as the standard, right? So you often see micron on the axis. And here's the measurement scale, so angstrom, nanometer, 10 nanometer, 100 nanometer, and so on, centimeter. And then you have different rows. And this is designated size ranges, aerosol definition, typical aerosol size ranges, bioaerosols. What is bioaerosols? You see it already here, but what is a bioaerosol? It's a fixed term, bioaerosol. It's really, as an engineer, you don't see it so much, but what is meant by bioaerosols?
Like there will be some process of...
Yeah, it could be in terms of, for example, inhaling powders, then we would talk about, but here it's more to biology, really. So what is a bioaerosol?
the nanoparticles are...
Yeah, and exactly, the nanoparticles are biological, so what kind of particles are these? Yeah, bacteria, viruses, and so on. And during Corona, we learned a lot about the impact of bioaerosols. They're traveling, right? And we can use all the theory we have to understanding the behavior of bioaerosols, at least when it comes to spreading and these things. So then there are sampling definitions. We will see this in a minute. And just as a comparison, here's the wavelength of electromagnetic radiation, so X-ray, UV, visible light, and so on. This is very, very important when it comes, for example, to measurement techniques, right? Light scattering and so on. And it's also important because we are in the same size range, and the properties changing if we are below or above visible wavelengths. So if we take a look, aerosol definitions, and these are terms you have heard but probably never thought about it, but basically I will not go through the definitions in this class, but it's just important that you know that fume is something different than dust, than fog or smog, okay? And we have sprays and cloud droplets and smoke, and the Friedlander book is called Smoke, Dust and Haze. And it's aerosol topics, and the beginning of the research was, so it was in LA, and they had a lot of problems with air pollution, okay? So, and in air pollution, smoke, dust, haze, these are very, very important findings, and this is strongly recognized to what we're doing here. And I will talk in the seminar, but just as a hint, I don't know if it's a surprise, but one of the seminar will be shifted to the afternoon because we will have an online meeting with University of Minnesota. And you are grouped with students from the University of Minnesota for one seminar, and they are making urban planning, okay? So I will talk later about it, but we are planning this now that one of the seminars will be online with University of Minnesota together, okay? It's kind of a surprise. I don't know if it's a surprise, but I mean, it's voluntary of whom from you who want to know, but one of the seminars will be together with University of Minnesota. And this is because they are talking about urban stuff, cities and so on, but this is the connection we have, okay? This smoke, haze, and so on. Then we have here typical aerosol size ranges, and here you see now already the industry, okay? Flour. Who knows I think it's Rolandmühle in Bremen. You know it? Okay, there was a big explosion, I think in the 70s, because there was a dust explosion from flour, okay? So if you have too many particles in the air, and then you have ignition, and then it makes boom. What happens in a dust explosion? Flour normally doesn't burn, but why does it burn when it's in the air? Suction, no, there's something else happen. Why if I have flour just here and I try to burn it, it doesn't work, but if I would just put it in the air, it would burn. Yeah, I need oxygen, right, for the burning, but why? I mean, I don't change the oxygen in the room, but what do I change? Yes and no, because I don't change the size by just distributing it in the air. You're right, something is blocked, but yeah, the surface of the particle contacting the air. And when I distribute it in the air, there's enough oxygen for burning, but if I just have it here, it's kind of blocked. Or so there's not enough oxygen feed for the burning. So this is extremely important when it comes to aerosols in the air. So there's a safety point. Coal dust, flour, coal fly ash. Fly ash is a very important material in concrete, for example. Then here, tobacco smoke is so important because I showed you the picture last week, right? You will see the picture today again, and we will make a small exercise about tobacco. And tobacco is really important because if you see here, where is it? I'm looking for one specific. Yeah. So this one here. Free molecular, transition, and continuum. And you see tobacco is in this transition regime. What is continuum regime? What is meant by continuum? So this is now designed size ranges. So now we're talking just about size ranges, not about a specific material like flour or fly ash. But there's continuum, and then we go smaller, then we're in transition, and then we are smaller in the free molecular. And tobacco is exactly in the size range of transition. But what is the meaning of continuum? You used it already in your bachelor. You should know what a continuum is. Where did you use continuum theories or continuum? To what could it be related? Make a guess.
Medium, for example, the
Yeah, yeah, very good. So the whole medium. So basically, continuum means you have a fluid. So normally, continuum is for fluid mechanics, okay? And you have a fluid, and the fluid has homogeneous properties. The density, I mean, there could be a temperature distribution, whatever, but these things are continuously. And you don't describe a fluid by molecules. You don't care about molecules. You just say, okay, water has homogeneous properties, that's it. You don't think about water molecules. And this makes calculations very, very easy. However, the smaller you get, the more questionable this assumption is, right? Because if you get smaller, 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 what you normally not do in fluid mechanics, because you calculate an airplane or a pump or whatever, but if we here now go smaller to the nanoscale, it's really questionable if you can describe water just by water, or if you not have to consider molecules. And this is what happens here in the free molecular regime. And here you cannot describe water by continuum, but you have to describe it by probability of molecules, okay? How they move. Kinetic energy is not a temperature, it's kinetic energy, and they move somehow randomly and these things. And we are touching this with our nanoparticles or nanoaerosols. And there is something called transition, and this means they are not so small, or it's much too complicated to describe it molecule by molecule, because then you have millions of molecules. But it's also too small for continuum. And tobacco smoke is exactly in this size range, and this is the reason why we can smoke it. If not, we couldn't smoke it. Okay. Then you see here diesel smoke from engines, so engine aerosols. And what I also really like is sea salt, because sea salt is something you probably never thought about it, but sea salt is very interesting about how to make aerosols, because they come out of the water, right? Somehow it comes out of the water, and then you really see, when you're on the sea, you get these on the skin, right? And you also have it on the tongue. So this is traveling aerosols from the water to you, and that's everywhere in the air. So sea salt is a very nice and interesting example to understand how aerosols move and how they are formed. Okay. Then we have here also two definitions, PM10 and PM2.5. Do you know what PM10, PM2.5 means? Yeah? Yeah, and why 10 or 2.5? This is kind of definitions we use in health, okay? PM10 means so and so much percent shouldn't be smaller than 10 microns or smaller than 2.5 microns. And with this, we can define concentrations which are not dangerous, okay? Like normally PM10, I think, is the average over a year is 40 micrograms, which you on average should breathe in and breathe out, not more. I think for PM10, but we will see it in the example. Okay, so these are definitions for health. And then you see thoracic particles, and these are the particles which go in and could go out. Okay, so now I talked a lot about this diagram, but I think it's really important, and I always recommend you from time to time to look at this diagram to just get a little bit an idea. And I want to give you now a very simple example with a small experiment. I think a few of you already have done the experiment with me. I have chocolate here. Who has not done this experiment with me? Okay, then you are the lucky guy who gets 2 pieces of chocolate, and you have to taste them. And you didn't do it also, not? Okay, so you can also give him. And I want you to eat both of them and compare them and tell me how they are different, okay? And don't tell me the taste is different, because this I know, but that's not the point. Because the one has a lot of cacao and has no milk, and the other one has milk. Okay, there's milk. I hope if anyone, okay, it's with milk, okay? So it's not vegan or anything. So then you just can. Do you eat milk? Do you eat milk? Okay, then you make the experiment. Okay. You have to compare both. You can just eat one of them if you want. But then I want to have a second person who eats milk. And okay, then you can both. There's enough chocolate for everybody. Okay. Just taste it and tell something about anything you could describe what you feel when you eat it. So you ate the one with milk, right? And now try the other one and compare them. Are they complete the same? No. Okay, what is different than taste? I know taste is different, but what else is different? Okay, it was really bitter. Okay. It was melting slower. Very, very good. Melting slower. Good. Melts easy. Okay, so there's a difference in melting. What else? Did you appear anything else? Okay, so the one with milk is very soft and very smooth. Okay. Yeah. So it doesn't melt so fast. You also said the one with cacao takes more time to. Okay, very good. What else?
Like after having witness,
Yeah, very good. So it feels dry without the milk, right?
like with milk, it's not like
Mm-hmm. It has more structure or texture. Yeah, yeah. And so basically, what you tell, a lot of people tell, so the melting is different. It's drier, and also the one without milk is more sticky. Okay, I don't know if you have appeared it. I mean, it's from, but the one with a lot of people say it sticks more to the teeth, or it doesn't distribute so homogeneously as the one with milk. Why it's this? Why it's like this? Why they are so different? Okay, so the milk has an influence due to the surface tension. Actually, I cannot say much about it. But what you have to consider, milk is in terms of a powder in there, not as a liquid. Okay, milk as a powder in the chocolate, and cacao is a powder. Actually, there are two things why I really like to make this experiment, because I mean, it makes one point, we will see in a minute, but there are two things about chocolate, especially whom of you likes the really dark chocolate, the one with a lot of cacao? You like it? Very good. Why it's good to like this very dark chocolate? It's very good for health, and it makes happy, basically. I mean, not from one of the other day, but the dark chocolate is very healthy and makes happy. And the civilization, there are older civilization which had a lot of cacao in their natural, I mean, not the sugar cacao we eat today, but they don't know any issues with heart circulation problems, or they don't have it, okay? And all this comes to the chocolate, comes because of the sugar, okay? So, but the cacao itself is very, very healthy. So get used to the dark chocolate, and then you have a healthy sweet, which makes you also a little bit happy. So how is cacao made? So we have we are engineers, chemical engineers, so we think in terms of unit operations. So this is what is done locally. And there are a few countries who harvest cacao in terms of these fruits. And then there are other countries, like Germany, for example, who make a lot of money by processing this. And so you see, it's quite simple: harvesting, fermentation, then we have drying, which could be outside, bagging, transportation, and that's it. And then at one point, when it comes here to the industry, then we see, okay, winnowing. So what happens there? At one point, we have these cacao beans, and then they are crushed because they have a shell, and they have an inlet called nib. And we want to have this nib because this is what basically can be used for the chocolate. And there we use very basic mechanical unit operations for crushing and winnowing. Winnowing is something, separation. What is winnowing? How do I separate particles in winnowing? Yeah. It's kind of a sieving, but sieving is very specific. I mean, both of them are separating, but which mechanic is winnowing using? They use air, that's correct, but not like a centrifuge. They use air in a different way. How is it? It comes very close to a fluidized bed. It's not a fluidized bed, but the mechanic is similar. So basically, you separate by density or something, right? So you have an airstream, and the heavy particles fall down, and the light one goes mid. So if you crush, the heavy shell will fall down, and the rest will just go with the airstream, and that's a very simple separation process. And then we have these nips, which are kind of the value product. And then it's roasting, so we want to have flavor, right? So the flavor develops, And then it goes into grinding. And this grinding is just making the roasted nips smaller. And then we get already this liquid cacao, which is like a dry mass. And this dry mass now goes in the important step here. Because these particles are larger than 30 microns. And larger than 30 microns, it means it can be detected by your tongue. And in the chocolate, you don't, or the producer, don't want that you really feel these grains. I mean, the texture you feel is not the single particle, okay? And in the last step, which is here, refining, grinding, and conching, they grind again, and afterwards conching, or sometimes grinding and conching together. The grinding, you go below 30 microns. And now it's different if you have dark chocolate or if you have a milk chocolate. And there the size of the particles is different. And that's what you see here. These are size distributions for milk chocolate and for dark chocolate. And this is here a cumulative size distribution, and we will learn about this later. And you see this one, here's the size of the particle, right? And here you see it even more. The large particles are used in milk chocolate. And for dark chocolate, you grind longer to have fine. And these differences you explained with very dry, sticky, melting behavior is related to the particle size. And for dark chocolate, which is quite expensive, they want to have a feeling, right? So they want you to make an experience, and they can adjust it by this unit operation here, grinding and conching, which will lead to a difference here. And this is what, at the end, you feel in the mouth, okay? So it's a very simple, maybe a little bit oversimplified, but I think clear example how you can see how important the particle size is to change properties of a product, okay? And also how to deal with the value of particle sizes. So this data here is extremely important, okay? To make the selling point of the chocolate. And there are a lot of other examples, of course. What is this? Yeah, it's a mice. So it's testing mice. What could be tested there? Which kind of particles? Yeah? Yeah, nanoparticles, that's correct. Because if not, it would be hard to travel to the body, right? Or micron could work. But what kind of particles? Look at the company. Yeah. What is in the vaccine? What kind of nanoparticles? No, not a bioaerosol. What is in the vaccination? Yeah, not bio. Actually, I'm not so good with this definition. Maybe you are right, but I want to point to something specific. So I cannot say yes or no in this case. But
Maybe since it's biotech, dead viruses?
yeah, mRNA, a kind of, it's not a dead viruses. That's the different vaccination. Now we go into something I really don't know. But what is the problem with the mRNA? Is it stable? So we can produce mRNA, or they can produce mRNA. Is it stable in our body? No. So if we put it in the syringe and put it, it would be destroyed anyway. So how do we make it stable? Because it had to go to a specific part in our body. So if you make the vaccination, the medicine has to go somewhere to be active. So how can we play around? You should know, you read the book. Yeah, make it stable with the shell of what kind of nano? Lipid nanoparticles, okay? So lipids are very good to surround the mRNA, and basically it's nothing than a protection, okay? That the nanoparticle is long enough stable that the mRNA can go into the cell, and there the process can go down. So, and I'm not sure if a lipid nanoparticle is a bioparticle or not. Actually, I don't know. We have to ask people, chemists for this, or biochemists. But the point is the lipid nanoparticle. So what do you see now on this slide? You see mice with colors. The used lipid, exactly. So basically we see differences, okay? So you see the spleen, the liver, and the lung. And you see that here, preferential targeting lung. So this means these mice are target, or the lung of the mice is targeted by the lipid nanoparticles. And here, preferential spleen targeting. And here you see that most of the particles go into the spleen, and most of the particles here go into the lung. So it's really, so by making the syringe, the vaccination, it's somehow, by doing some magic, possible that the nanoparticles go into the spleen or the lung. Why do we want this difference? Because it depends on the kind of cure that you need the vaccination in the lung or you need the vaccination in the spleen. So as far as I know, for the corona, we need it in the spleen. But I'm not a medicine guy. I just know we needed to have somewhere specific. How can we make this, that the medicine not just travel around, but goes to a specific part of the body? How can we do this? Yeah? Exactly. Each cell has a different door, size, and this means when they're going, the size depends where they can enter and not. And some of them are 60 nanometer and other are 300 nanometer. I always mix up which is which. I don't know. I think the lung is 300 and the spleen is 60 nanometer. It could be vice versa. I don't know. So look it up and correct me if you know it. But by the size of the particle, we can adjust where it goes. It's a very simple method, right? And this is what I really, really like, because here you see that, okay, mRNA and all these things, very, very important, very complicated. We don't know much about these things as chemical engineer, but adjusting particle size, this is something we can do, okay? And this seems to be very important, and it's not so trivial. How to do it, and there are different methods, and one method I would like to show you here, liposome production, and this is this production of lipid nanoparticles, and this is something called microchannels. I don't know if anybody of you have worked with a microchannel so far. So in Delft, where I'm also teaching, they have very nice lab with microchannels, and they can do all these kind of experiments. And what you have here is you have an alcohol, and in the alcohol are the lipids, okay? And then you have a buffer solution, and this buffer solution is surrounding the alcohol in the channel. And at the interface of the buffer solution and the alcohol, you can create the particles are formed. They are forming at the interface. So you have two liquids, and here you see the inlet in the microchannel, zack, 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 so different inlets. And here the reaction, at F, the reaction takes place, okay? And it's important to understand this picture on the right side. So the microchannel is here, okay? This is the microchannel. And this one, this colorful, is in the middle, is the alcohol stream with the lipids, okay? And surrounding here and here is the buffer solution. So it's not, the channel is not going here, but the channel is going here, where it's really dark blue. I don't know if you can see the difference in the light, but I will mark them, okay? When I upload the slide, I will mark them. But it's important for you that next to these colorful left and right is still a stream, okay? And what is changing is the ratio of the two streams. So here is a lot of IPA, so isopropanol, and the amount is decreasing. But the volume flow rate is the same for all 2, 4, 6, 7 experiments, okay? So the amount of overall liquid going through the channel is the same, but the ratios are different. And this is something very easy to adjust, okay? And here are the results. So the left one is that the ratio is constant. So you take, for example, this picture here, and you change just the amount, so more or less liquid. And if you do this, you can make a little bit more or less nanoparticles, but they are always the same. Okay, the size distribution of them is always the same. So you make always the same nanoparticles. However, if you play a little bit with the ratios of these two streams here, the buffer solution around and in the middle the IPA, then you can adjust perfectly the size and the weight of them. So if a company says, I need 300 nanometer, you could make it. If they say, okay, we need 60, you could make it, okay? And this is very, very nice chemical engineering of adjusting particle size, and here is the use case directly, okay? And this is done on a lab, but of course microchannels easily can be scaled up, and the problem is the other process, which is normally done because this is the research, is you have just a vessel, a mixing vessel, but in a mixing vessel it's very heterogeneous, and this means you create all kind of nanoparticles, and this means you need additional unit operation to narrow the size distribution and catch the one you would like to have, while here you just adjust the two liquid streams, and at the interface, because it's laminar flow, it's perfect condition in terms of homogeneity, it's not a heterogeneous system, and then you adjust the particle sizes as you want. And this is, for me, very nice chemical engineering related to this application. And the third one is here as an example, and this is, what is it? Take a look and tell me what you see here. You don't have to read the full text, just 1, 2 bullet words, yeah? Yeah, nanopowders using in batteries, lithium oxide, lithium metal oxides. And it's what I really like here, it's a patent. The patent is not very old, 2022. So the present application is related to an improved method of forming fine and ultra-fine powders and nanopowders. So this is a production method to make these nanopowders. More specific, invention is related formation, blah, blah, blah. Lithium metal oxide. So it's about to making these lithium metal oxides, 2022. Why we need new methods, and they are pointing out here. These materials, blah, 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 are more expensive to produce on an industrial scale, so relating to the lithium metal oxides, due in part to the necessity of nano-sized materials with a narrow particle size distribution, high porosity, high surface area, and other. So here it's clear that they say, okay, we need a narrow size distribution, and we need a process who can give us a narrow size distribution, because this is what we need in our product, okay? Last week, we had the other example. We had a wide size distribution. Also there, do you remember this? Where was this with the wide size distribution? Last week, what was the material we talked about?
Carbon black.
Yeah. And they said, so carbon black, and there was a flame reactor designed to make a wide size distribution. Why? Because wide size distribution gives better packing of the particles, right? Less gaps. And it was made for black ink, and black ink needs good packing of the particles to be very intense and very black, right? And here we want to have the other way around. So it's again the size distribution, and we want to have a process who comes up with a narrow size distribution. And they said, okay, they have a process. This seems to be very important in the batteries. And what I really like in the patent, they give this overview. And I really like this diagram. And they said, yeah, they are a conventional method. The solid state is a conventional method. And I saw this in industry. They are really using it. And if you're interested in it, Thomas Juste is doing a lot with this, because all these particles he's doing, they are doing with solid state sintering, which is a really good process because you get high purity, but you also have high cost. And one very important thing is that in solid state, you kind of crush the particles, then you mix them, then you sinter them. And then you have the problem that you get a very broad polydispersed size distribution. And this means you have to crush and separate the particles, okay? So here it's milling and grinding, and then again separating. And you have to do this again to sort out the ones you don't want to have, okay? And this is very expensive, very energy expensive, and you don't want this when it comes to a scale up. And they said, okay, this is how we do it, but there should be better ways. And they developed it, what they call here a chemical process. We will get to know this more details in other lectures. I will not tell you too much, but at the end, it's a nice reactor with a stirrer, and that's it. And they have a 3-phase system in there. And say, okay, this is now the holy grail, how to do it. And they said, okay, there are also other processes, and this is listed here. And they said, okay, these processes are basically better in giving a narrow size distribution than the solid state process, but this is not scalable. Okay, so Sol-Gel, for example, is a process where you need a lot of liquid. And then you have a lot of liquid which you have to handle afterwards. However, CVD, in my opinion, is a scalable process. And funnily, you don't see the flame reactors here. And that's different from a patent to a scientific application. In a patent, you don't have to be complete. You just make your point, okay? And flame processes are perfectly for scaling, and they also make these oxides by flame process, but you just don't find it here. That's it, to make your point. That's the difference from a patent to a scientific. In a scientific publication, the reviewer would say, there's something missing in your comparison. And in a patent, you don't have to do it. Okay, this is the last example, and then I would like to go a little bit into the theory, but before I would suggest to make a 5-minute break, okay? And then we make half an hour, 45 minutes of theory, and then we make the lunch break, okay? So we will make 5-minute break.